Inside the solid resin of a high-voltage insulator, an air pocket no larger than a grain of sand is trapped. Under extreme electrical stress, the gas inside this void breaks down, producing a violent flash of electricity that remains entirely contained within the pocket. This is partial discharge, or PD. International standards define it as a localized dielectric breakdown of a small portion of an electrical insulation system. It is an electrical short that only partially bridges the space between two conductors. These individual events are fleeting. A single discharge pulse lasts only fractions of a nanosecond, transferring a minuscule amount of energy across the void. But that nanosecond flash exerts an immediate physical toll. The spark releases a localized burst of heat, ultraviolet radiation, and a mechanical pressure wave into the surrounding solid material. A single spark causes negligible damage. However, these discharges repeat thousands of times per second, aligned with the alternating current of the power system. Over years, millions of repetitive microsparks chemically and thermally erode the insulation. Look at the scale of the infrastructure required to distribute power. Transformers, switchgear, and miles of high-voltage cables represent millions of dollars in capital investment. The integrity of these massive systems relies entirely on the perfection of their internal insulation. A single microscopic void, a manufacturing impurity, or a slight delamination inside these giant structures is all it takes to harbor a discharge. Left unchecked, the continuous erosion from these tiny sparks bores through the dielectric material. The discharge gradually carves branching, carbonized channels, known as electrical trees, deep into the solid insulation. Once those carbonized tracks bridge the gap between the high-voltage conductor and the ground, the remaining insulation collapses completely. The result is a sudden explosive flashover and an immediate grid outage. This presents a specific engineering challenge. To prevent grid collapse, operators must detect and pinpoint a microscopic hidden spark from the outside of a massive, heavily shielded high-voltage asset. Discharges are classified into three variations: internal, surface, and corona. Internal discharge occurs in microscopic cavities, aggressively degrading solid insulation. Surface discharge tracks across contaminated solid-liquid interfaces. Corona discharge happens in gas around sharp metallic points, generating corrosive ozone. Engineers model this electrically. In this equivalent circuit, Ca is the total capacitance, Cb the healthy insulation, and Cc the gas-filled cavity. As alternating current is applied, voltage stress builds across the weaker gas in Cc until it breaks down. This defect acts as a tiny capacitor in series with healthy insulation. It continuously charges and violently discharges against the alternating current, generating high-frequency pulses. Because this tiny capacitor is permanently sealed inside layers of solid insulation, the actual electrical charge transferred during the spark cannot be measured directly. The IEC 60270 standard defines a circuit measuring apparent charge. When the void collapses, the test object's voltage drops. The coupling capacitor, Cb, transfers a compensatory charge, creating a transient current that the measuring impedance, Zm, converts into readable voltage. This measured apparent charge is expressed in picocoulombs. 1 picocoulomb is 1/trillionth of a coulomb. We are not capturing the exact energy of the microscopic spark. Instead, we are measuring the precise electrical echo it forces through our diagnostic circuit.
The conventional IEC 60270 method is highly sensitive, which is an advantage in a controlled laboratory. But in a live operating substation, the circuit picks up background electromagnetic interference, obscuring the actual defect signals. To cut through the noise of a live grid, modern diagnostics capture other physical byproducts of the discharge, specifically electromagnetic radiation and acoustic pressure, rather than relying solely on electrical current. Ultra-high frequency, or UHF, sensing is the primary non-conventional method. These sensors detect gigahertz range emissions, bypassing lower frequency noise generated by external corona discharges. These sensors can be deployed on live, sealed infrastructure without physical modification. A UHF sensor can interface directly through an existing oil drain valve on a transformer, acting as an antenna inside the tank. Fusing traditional picocoulomb analysis with high-frequency electromagnetic and acoustic data allows engineers to isolate the exact degradation signal, regardless of how electrically noisy the surrounding environment might be. Knowing the magnitude of the apparent charge is only the first step. To assess the actual risk of failure, engineers must identify the specific physical nature of the defect causing the spark. This PRPD chart plots apparent charge against the AC cycle. Corona discharges form sharp triangles at the voltage peaks. Surface discharges produce asymmetrical crescents along the edges, while internal voids generate elevated arcs on the rising edge. PRPD analysis takes millions of overlapping nanosecond pulses and organizes them into a diagnostic fingerprint. It visually decodes the precise physical geometry of a defect buried inches deep in solid resin. Capturing these PRPD fingerprints requires different diagnostic strategies depending on whether the high-voltage asset is isolated from the grid or actively under load. In offline testing, the asset is disconnected from the network and energized by an independent external power source, such as a very low-frequency tester. This controlled environment allows engineers to measure the inception voltage, the exact threshold at which the applied electric field first causes the internal gas to completely break down and spark. Online testing leaves the equipment connected to the live grid. Non-intrusive sensors monitor the asset continuously as it operates under normal electrical, thermal, and mechanical stresses. Offline testing maps the baseline physical characteristics of the insulation. Online monitoring tracks how microscopic flaws react and degrade over time while actively powering the grid. A common misconception in partial discharge analysis is that a specific picocoulomb value dictates that an asset is about to fail. Because the measurement is an apparent charge, altered by the physical distance from the defect, signal attenuation, and sensor bandwidth, an absolute reading in isolation provides very little context. This chart tracks the only metric that dictates action: historical trend over time. A stable, flat discharge level indicates a dormant flaw, not actively eroding insulation. The warning sign is the curve. Rapid acceleration in magnitude confirms active tracking. Breakdown is imminent. Detecting that curve before the insulation fails is the difference between a controlled repair and a catastrophic regional blackout. By fusing the fundamental physics of apparent charge with PRPD pattern recognition and continuous online trending, grid operators no longer wait for assets to explode. They track the invisible spark, predict the breakdown, and secure the grid.